Hello there, I'm Tiffany from Tokyo. Thank you very much for having interest in my presentation, and thanks a lot to the session chair and organizer for allowing me to speak at this wonderful conference. I'm very excited to talk about Condom, a new software for in silico design of mutagenesis libraries. First of all, please let me give you a brief introduction about AISD. AISD is one of public research organization in Japan. Our AI Research Center is a new center of AISD, and my own team is a fusion of biotechnology and IT. Our research-based AISD Tokyo Waterfront is located on an island in Tokyo Bay, which will host 16 games of the Tokyo 2020 Olympic and Paralympic. Like other speakers in our session, my team is also working on multiple approaches to apply AI to protein engineering. This is a typical cycle: design, build, test, and learn to improve protein function. When we finish the first cycle of DBTL, we obtain a list of promising sequences which need to be tested. We would like to test our most promising sample as many as possible with low cost. Would lead to generate a mutagenesis library with specific amino acid profile. Even this problem was partially studied by a couple groups since 20 years ago. No in silico tool was available. Therefore, we decided to develop a new tool for public use. Let's take a look at this problem from the starting point. Here is a standard codon table. It contains 3 positions of nucleotides. For each position, there are 4 possible nucleotides. So totally, 64 possible combinations encode 20 amino acids and 3 stop codons. In protein engineering, for mutagenesis library, we often use multiple codons. We describe a mixture of multiple codons as codon nucleotide composition. In this presentation, I use beta AIChE to formularize the frequency of nucleotide I at position J. Generally, there are 15 IUPAC codes for typical frequency of nucleotides, as shown in here. Maximally, we have 3375 IUPAC degenerate codons. Now is the first problem, how to calculate an amino acid profile from a codon nucleotide composition. For example, this is codon nucleotide composition of NNK. As shown in this slide, we can easily calculate frequency of possible codons and identify the amino acid profiles. So how about the reverse problem? Given an amino acid profile, how to identify its corresponding codon nucleotide composition? You might see that this is not easy since it includes multiple variables. We approach this problem as an optimization problem. We take the input as the desired amino acid profile. For an amino acid A, we define the frequency at T-A. The output contains calculated frequency of amino acid become A and the corresponding codon nucleotide composition beta AIChE. Our optimization problem aims to minimize the mean square error MSE between the desired and calculated amino acid profile. This problem comes up with several constraints of related parameters, as you can see here. To solve this nonlinear problem, we use IPOP developed by CMU as a solver. We name our solution as Condom AIChE. Condom AIChE were written mainly in AISD, and we put it on GitHub for public access. In the current version, we provide several different setting options, such as 4 programs with different constraints about stop codon, global optimization search, and minimum guaranteed threshold. Next, I would like to introduce how codon adjust works. We take the first question, whether codon adjust can minimize MSE between input and output. In this task, we use the on-stop program and run it with NNN. For small data, we take antibody binding site CDRH3. This input contains 14 positions. Here are the results of cyclogo as well as MSE. The gray and red represent the initial and optimized MSE, respectively. As you can see, MSE of the output is extremely smaller than the initial one, suggesting the good performance of codon adjust. Then we check if the same result would be observed with the big data input. We use PFAM database with more than 4 million of positions. The result is here. It shows significant improvement of MSE after minimization, which again demonstrates the performance of our software. In the next task, we verify performance of 4 programs, namely on-stop, no-stop, TAZ2-stop, and TAZ2-glutamine. Here's the table of 4 programs and TAZ, TAA, TZA restriction. On-stop allow on-stop codon. No-stop completely restrict on-stop codon. TAZ2-stop limit TAA and TZA, but allow TAZ. Finally, TAZ2-glutamine is targeted for customized translation table where TAZ is translated into glutamine. In this task, we take CDRH3 and NNN. Here are results from cyclogo and MSE. Gray is initial, red, green, light blue, and dark blue are on-stop, no-stop, TAZ2-stop, and TAZ2-glutamine, respectively. You can see that codon adjust successfully minimize the MSE for all programs. Here are frequency of TAZ, TAA, and TZA. We confirm that this codon appear in the output when being allowed and disappear when being restricted. Taken together, the results show that codon adjust work correctly as setting. In our optimization problem, there is possibility that instead of global minimum, local minimum is found. In most cases, codon adjust outputs global minimum, but with very strict conditions like no-stop program, sometimes it also outputs the local minimum. Here's one example. You can see why tyrosine is measured in the input. It totally disappears from the output. This is unexpected but understandable since the no-stop program restricts all stop codon, which tend to separate adenine from the second position, causing no frequency of tyrosine. We address this problem by utilizing different initial values and looking up for the global optimum from all the outputs. We exploit 3375 AIChE degenerate codon, which cover the whole space of codon nucleotide composition. This is the setting of the next task. The results for position 12 and 14 are shown on the bottom right. On the further optimized column, MSE are distributed with success occurrence of local optimization at both positions. We take the smallest MSE in the box as likely global minimum. In this way, by using all 3375 AIChE degenerate codon as initial values, Condom users can find the likely global minimum of NSE. Another issue of the optimization problem is amino acids with major frequencies are possibly prioritized, which may cause no appearance of minor amino acids in the optimized mixture. Therefore, we provide one more option, the control factor CF, which specifies the minimum guarantee of all amino acids. This is the setting of our task. We compare the result of Condom users with CF0 and 0.1. With CF0, there is no lower bound of the output, while CF0.1 requires the output to have at least 10% of the input. Here is the result of position 13, which shows the ratio of the output to the input. The green and blue represent CF0 and 0.1 correspondingly. The red line shows the baseline of 10% of the input. With CF0, there are 4 amino acids with frequencies lower than 10% of input. Meanwhile, with CF0.1, all the amino acids was equal or higher than 10% of input. Additionally, we also confirmed that the MSE was almost the same level as the CF0. So overall, the result demonstrates that control factor option is an effective method to automatically control the amount of output. Finally, as in comparison with previous methods, we look at the skew codon. The skew codon was known to be able to mimic the amino acid profile of CDRH3. This graph shows amino acid frequency of the M library and library generated by skew codon. We can observe that there are big differences in several amino acids such as A, C, Z, H, and so on. This graph contains the amino acid profile using our optimized Condom nucleotide composition. The differences between input and output are clearly improved by Condom users. We also compare MSC of the two methods and verify that Condom users decrease the average MSC compared to the skew codon. In summary, the data suggests that our optimized Condom nucleotide composition outperforms skew codon. So far, I have introduced Condom Aisd, a new software to design Condom nucleotide composition. We made it available on GitHub for everyone with the hope that it can be helpful to your research. If you have any questions, please feel free to leave your message in the chat box. Lastly, I would like to thank my team, collaborators, and all organizations for supporting me in the development of Condom Aisd. With that, thank you very much for your kind attention.